Okay, welcome everybody to our next Expedition in AI seminar. Today we have Giulia Menichetti, a senior research scientist at our Network Science Institute, and also associate researcher at Brigham and Women's Hospital in the Harvard Medical School. And this will be the first seminar where we put together AI and complex networks, and the topic will be the Foodome project, and to see basically the complexity of food system. Giulia, the floor is all yours. Thanks for coming.
Okay, so thank you so much for inviting me. I think this is a great opportunity. So let me share my screen and then we can start. There you go. So can you see my screen? Yes, no? Someone speaks, please.
Yes.
Anyway, so hi everyone. Thank you for the introduction, Ricardo. I'm Giulia Menichetti. I just started as a junior faculty at Harvard Medical School, but I'm also at home at the Network Science Institute at Northeastern University. I lead a project called Foodome between Northeastern University and Harvard Medical School that aims to track the food chemical complexity of the food we consume and understand its mechanistic impact on our health. But now the project has spread all over the different layers of the food systems, reaching all to public health interventions. A little bit about me. I'm not a computer scientist. I'm a physicist by training. And before leading this group, I studied statistical and computational physics, and I specialized in network science. My major implication of interest was in biological networks, and my research spanned from the stratification of cancer patients, as well as aging, to the variability of the response of patients to drug. And well, first of all, a reminder of why we're doing what we're doing. So let me remind you why we care about including nutrition in our mechanistic investigation of health. In other words, the reason why we started this project. When I joined the Barabaji lab at Northeastern University, in the first discussion with Professor Barabaji, we pointed out a major problem of the network medicine framework. And this problem was that nutrition was out of the picture. However, nutrition is the leading factor for the #1 killer in the US and also in the world, that is heart disease, as you can see here. And overall, only 10 up to 20% of US deaths are of genetic origin. That is the main focus of attention and therefore of funding. Last but not least, according to a 2021 report on the true cost of food published by Rockefeller Foundation, the US incur yearly on $1.1 trillion in food-related human health costs. With direct and indirect costs for cardiovascular disease and hypertension too, leading basically the statistics with more or less $382 billion, and followed by obesity and overweight that are around $359 billion. So this is amazing. On the other side, we can go on without stressing that a key word in the description of the Foodome project is complexity. And what an incredible year was last year, 2021, for complexity. This is the first time that complex systems were explicitly mentioned in the Nobel Prize ruling. And on the other side, I don't think this is the place to discuss the reliability of climate models or how to model, for example, frustrated systems, but it's an occasion to discuss the core of this research and the core, for example, of the Network Science Institute, that is that in complex systems composed by many interacting components, simple behaviors can give rise to complex collective phenomena with similar templates, from physics to biology, social systems, and of course, machine learning. Consequently, complexity science is strongly interdisciplinary. The focus on interactions naturally brings the concept of network thinking that you can see here and network science. And by network science, we define the science that by modeling how entities connect is able to predict the collective behavior of the system. At the root of this interdisciplinarity, we find how mathematical rules behind these interactions are usually way more predictive than the features characterizing the single entities, or what we call nodes. But let's go back to nutrition. How do these concepts apply to nutrition? Well, complexity in nutrition is really everywhere, from disease phenotyping, so the concept of disease and health, for example, connected to the framework of network medicine, to the modeling on nutrient bioavailability, bioaccessibility, and finally to the concept of food matrix. But first, we need to clarify which entities are contributing to the food systems. So step number one in complex system modeling is mapping the key players and their interactions. Let's start from the micro level with the chemical composition of food. Given our initial expertise in network medicine, we had expectation for naturally occurring compounds and also additives that was very similar to drugs. For drugs, we have extensive records describing their presence in food with quantified amounts and interaction with known human protein targets. Unfortunately, we soon realized that this scenario was very far from reality. And we collected our initial insights into a perspective piece that you can see here, where we define as the dark matter of nutrition all the chemicals present in food and largely invisible to both epidemiological study as well to the public. At the same time, while we were writing this perspective, in open source databases, we found approximately 26K chemical compounds, small molecules mainly, sparsely distributed across different foods. After significant efforts in data integration and disambiguation, combining annotation from the scientific literature, from experimental repository of mass spectroscopy, and aggregated databases, and finally also genomic and pathway interactions, we recently reached 135K chemical compounds, and we keep growing. So there is definitely a very long road ahead of us. And as you can see on the left, despite the fact we have collected annotation for more than 3,500 foods, our chemical knowledge is unevenly distributed across the foods. Indeed, by looking into the cumulative distribution of the number of chemicals per food, we clearly observe jumps that are nothing more than batch effects due to the different types of available data per item. Around 100 compounds here, where you see the meatballs, we observe common dishes present only in national databases, such as the USDA. We then move to plants, for which we have a higher number of chemical available in the literature, so literature bias, but also extensive secondary metabolism, and finally experiments. And finally here, we reach plants, again, usually crops, for which genomic inferred annotations are available. They sequence their genome. Moreover, on the right, I summarize some of the results we had for metabolomic experiments on plants. Indeed, we ran metabolomic experiments too, so we're not only on the theoretical part. And we realized that we could expand the chemical universe even further, since the platforms like lipidomics that you can see here, CSH, for example, and also PFP, have limited overlap with the annotations in the current databases. That is, they are looking to a different corner of the chemical universe. Whenever you think about this type of experiment, you have to think about the capture and recapture experiments in ecology, different corners of the universe. And, it is not just this. The number of unknown peaks in the spectra, the part in red that you can see here, is between 56% up to more than 98%, and with an average around 80%, meaning that the spectra are rich in chemical information that we are unable to capture and translate. So to move forward, it is vital to extract information from these unknown peaks. Well, once we have mapped which chemicals are in food and their interaction with human targets, what could we achieve? Well, we could start predicting their effect on our health. As mentioned before, disease phenotypes and health phenotypes can be viewed as emergent properties arising from the crosstalk of molecular, metabolic, and regulatory networks at the cellular level. This is the framework of network medicine, of the so-called network medicine. For instance, each one of us has a slightly different interactome or protein-protein interaction network. That is the network that you see here in gray. And that expresses, let's say, our propensity for example, diabetes or any other type of disease. And these are the red dots, so the red nodes on the interactome map. According to whether a single chemical or a combination of chemicals, so that is basically food, are hitting this map, okay? So for example, for epigallocatechin, these are the targets in green. We can estimate the likelihood to observe an effect for a disease phenotype in a specific patient. This is an exercise that we did for polyphenols, plant-based chemical compounds, for which there are enough binding annotations. So there are enough green dots, let's say, and proved to work experimentally. We have also just submitted a paper where we started looking into, for example, functional foods. But unfortunately, naturally occurring compounds and additives are generally poorly annotated compared to drugs, and limiting our ability to apply network medicine right away. Indeed, there we go, only 4.58% of the nutrient dark matter, the compounds that I discussed before, has at least one known binding annotation with human targets. So we have a problem. We're just seeing how network medicine strongly relies on a protein target annotation, that is known binding links between chemical compounds and human proteins, and how this limits its application to food chemicals. This motivated us to understand better how a protein and a ligand bind in order to predict this type of interaction. Well, this process is very similar to the prediction of drug target interactions, so drug discovery, a critical step in drug discovery to reduce the failure rate of clinical trials. Predicting a drug target interaction is equivalent to study the likelihood of a ligand, what you see here in orange, to bind to one of multiple pockets of a protein, what you see here in gray. There are definitely traditional methods, very precise, like molecular dynamics or Dawkins simulation, that simulate this type of interaction. Unfortunately, these algorithms have very large computational complexity, as they require exploring all the possible location on the molecules. This is the reason why machine learning and AI, saw an opportunity, and they have been proposed as they require less structural details, and they have lower runtime, and they're also, very important, suitable for the screening of large chemical libraries like ours. So indeed, here on the right, you can see how the majority of these models leverage simple features known to drive the binding mechanism that are encoded in the amino acid sequence of the protein, or in the fingerprint of the ligand, the so-called Morgan fingerprint. While it is true that we lose information giving up the 3D structure of the protein, we gain the chance to screen larger libraries. And of course, we hope AlphaFold and Google to come and rescue us. So nowadays, we find many examples of algorithms that are built in a very similar fashion, to be honest. Like, for instance, the purpose here. There is an input that requires a minimal structural information like isomeric miles for ligands and amino acid sequence for the proteins. Then there is an architecture or black box where we learn the so-called embeddings, an optimal way to represent chemicals and proteins as vectors, and finally an output telling us the probability for a chemical and a protein to bind. This AI is trained, is educated, as I like to say, by observing the patterns of binding annotation from databases like BindingDB, where chemicals and proteins are reported with binding constants like dissociation and inhibition, and they're usually thresholded. So, for example, if the constant of interest is the constant of dissociation, or KD, if KD is less than a set threshold, we observe a positive link that becomes negative otherwise. This framework is, could be applied even to social sciences and in general to anything that has a sort of multiplex structure, so multiplex networks. overall, all these models, again, another problem of the literature, claim amazing good performances, and we want to trust them. So we chose their best performing architecture, and we started investigating the reliability of the prediction for naturally occurring compounds. Our focus on food chemicals is put us in a specific niche, right? We are interested in general in poorly annotated structures, and this pushed us to basically stratify the performance in 3 types of tests. The first one, transductive here, where the AI is predicting binding between molecular structure it has already seen. The second one, semi-inductive, where the AI is predicting binding between already seen ligands and never seen before proteins, and vice versa. And finally, the most important one, and toughest one too, the inductive test, where the AI is predicting binding between never seen before ligands and never seen before proteins. So a very important point here. Only inductive test performance should be used as the metric to evaluate the true performance of a binding predictor, as it tells us how well our model has learned binding patterns using the molecular features and how well it can generalize to new structures, exactly what we want. Otherwise, there is a chance that the model has just learned by heart from the list of annotations, disregarding the structure of the molecules. Unfortunately, what we've seen in the literature is that the majority of the papers so far offer only transductive performances. And here you can appreciate how the performance of the purpose deteriorates going from transductive to inductive. So why this has happened, and moreover, what has deep purpose learned instead of molecular features? Well, this goes back to the type of universe deep purpose has seen during training. Basically, it's like a syllabus for students in college. We realized it learned a topological measure, a measure driven only by annotations, quantifying the balance between positive and negative annotations that you can see here, of course, in the training data. This is what we call the binding degree ratio. And let me explain better what I mean by binding degree ratio. Here in this corner, I show the neighborhood of a ligand in the training set, this RIPK1, et cetera, that has a total of 3 annotations, 1 positive and 2 negatives. So degree ratio in this case is 1/3. We calculated this for all the chemicals and all the proteins in the training, finding that in both cases, the distribution of the degree ratio is bimodal, meaning that as you can see here, meaning that the training data lacks either binding or non-binding annotation for most proteins and ligands. And so this is why there you see accumulation close to 1, close to 0, and close to 1. These extreme values are what we call annotation imbalance, and this phenomenon raises due to the underlying network structure contributing to the training data. So you need to be very careful when you learn on a network structure, because there could be non-trivial biases in your data sampling. How did we confirm our intuition? Well, we compared deep purpose with a model coming from network science, a simple configuration model that is unaware of the structural features of protein and ligand molecules. The model relies on 2 layers, one for the positive links and one for the negative links, and is basically fixing the degree ratios observed during training. Yet, if we look into performances, it performs similarly to the AI models, showing the same patterns of transductive, semi-inductive, and inductive tests. This shows how deep purpose leverages mainly the degree information of protein and ligands in making binding predictions. So we started with the goal of using and creating a tool to predict binding for food chemicals, but in the meantime, we learned a lot on the issues of the current AI model in bioinformatics. So basically, we understood that similar to computer vision, where you have shortcuts emerging when AI models learn to identify the background of the picture and not the real object of interest, here we have the so-called topological shortcuts, meaning that our model used the degree ratio for predicting instead of using the node structural features, making basically impossible to generalize to novel molecular structures. In other words, the model is not really learning what we want and what it should learn. So we proved that annotation imbalance is associated with topological shortcuts, but where does annotation imbalance come from? Well, again, network science comes in help, and in binding data sets, kinetic constants, so KD and KI, our weights, are not randomly distributed across annotations, but on average, they anti-correlate, as you can see here, with the number of annotation per node. Moreover, the number of annotations are described by what? Guess what? A fat tail distribution. The combination between anti-correlation and fat tailness, so these two effects, drives the hub proteins and ligands too. So these are nodes with a very high number of annotations or records to have disproportionately more binding or positive records, while proteins and ligand with fewer annotation have more non-binding examples. So when we sample our data training uniformly, we educate our AI model with a very biased picture of binding. Consequently, we need to mitigate annotation imbalance, making the degree ratio less attractive to the eyes of the eye. And we want to push our model to learn the structural features instead. This is where network science becomes instrumental to AI interpretability, AI ethics, and AI fairness. So moving forward, how can we mitigate annotation imbalance? Well, we need to generate more negative sample in this case, as the database has only few non-binding examples. So as network scientists, we look into networks, right? And so here we can leverage the protein-ligand network formed by positive or binding annotation. So all those annotations that we consider there are binding for sure. So structure get attached somehow. So this is a network as it is displayed with pink nodes there are proteins and green nodes there are ligands. And on this network of all the structure that really bind, we calculate the short path distance between each protein and each ligand. We define as network-derived negatives all the pairs with high enough shortest path distance, right? So we basically use this network as a map. We do so because we first analyzed the average experimental kinetic constant as a function of the shortest path distance. And we observed that higher, let's say high path distance correspond to higher kinetic constants. And beyond 7 steps, the expected constant exceed 10 to the 6 nanomolar. And this is a way for us to say this is really not binding, or it's a very weak type of binding. You can see here this example where we are looking into a chemical and into a protein that are 7 steps away, and their constant exceed the 10 to the 6 threshold that I mentioned before. We found an ideal interval of shortest path distances where you exceed the constant of interest, so 10 to the 6, but at the same time, you're not sampling in the same network neighborhood. So you want to keep variability in your training. Then here you can find AI bind. This is the new pipeline we developed to maximize generalization and carefully drive the neural networks architecture to learn what we really care about, that is the structural features of the molecules. We made 2 main contributions that you can read here. First, we mitigated annotation bias by including both positive and negative examples for protein and ligands. And again, leveraging network science as we explained before, right? So this step is very important and improves the the training set in general, limiting the emergence of topological shortcuts. And then second, we also improve the overall structure that you can see here, learning the vectorial representation of molecules and proteins somewhere else, right? So not while optimizing the task. And we learned this into, let's say, bigger libraries that you can see here, where many structures are collected. They're not limited to those reported in binding databases. So in machine learning vocabulary, we call this an unsupervised pre-training of molecular embeddings. And here we can appreciate the result of the predictive performances. Well, first, as you can see here, the training, by fixing the training, we remove annotation imbalance, and so consequently the topological shortcuts. Our training sampling helps all models, not just ours, in learning binding from the molecular structures. And indeed, as you can see here, even deep purpose now works better than the configuration model. So it means it's paying attention to the right things. And second, the second jump here, AI bind shows the best performances since it uses unsupervised pre-training that improve generalization to unknown structures. Finally, we are at the validation point, of course. Well, we compare our results with autodocking simulations, so those methodology that I mentioned at the beginning. And in particular, we chose to screen COVID viral proteins and the related human protein targeted against, our compound library. We chose the top 100 and the bottom 100 and search for the available protein 3D structures. And this is the most annoying part, right? Well, what we observe is that the top binding predictions here show lower binding energies that compared to the bottom predictions. And basically, whenever we observe lower binding energy, it means that it's a stronger type of binding. And this is also significantly different, right? So the two distributions show remarkable different behavior. And also considering the binding threshold of minus 1.75 kilocal per mole, 88% of the top predicted pairs by AI bind are in line with the autodocking simulations. Additionally, another very cool result is that we found that the prediction made by AI bind and the free energies calculated from autodocking are anti-correlated. So this is the right sign, by the way, with a Spearman correlation of minus 0.51. And this is cool because the machine was not really trained for this, right? So in summary, we can use AI bind as a prioritization tool for autodocking, which requires significantly higher time to run. We have recently added an interpretability part that is helping in identifying the active binding pockets in a protein. And we do this by substituting basically each amino acid trigram in the embeddings with the null trigram. And then we observe basically the changes in the AI predictions. This works so well that we move on in creating basically what we call the auto-to-doc pipeline, where we use AI bind to prioritize the grid search of autodoc Vina. So please stay tuned because this is going to be out soonish. And so again, we created basically a tool at the end of the day that can help us in moving towards the network medicine framework. So then now for a moment, let's pause and, to take a bird's eye view on the food systems. So up to now, I have discussed only results on the biochemical characterization of food molecules. However, the ongoing efforts in mapping the nutrient dark matter and, and its molecular interaction with our body should not make us overlook the potential advances in nutrition policy and public health that would derive by applying machine learning to what is currently available, the data we have. Indeed, the biochemical characterization of food molecules, what I have presented to you so far, is just an angle. Usually, in our studies, we have to connect different layers of data that I've summarized here, and that's why also it takes forever to get published. There are four major groups. The first one is food composition, scattered a bit everywhere with different resolutions, starting with nutrition facts, so what you see in the grocery store aisles. The second one is food classification, key to understand the food behavioral aspect and to communicate scientific findings through public health and dietary guidelines. Third, we find the so-called macro level, all the cohorts to run epidemiological studies. And last but not least, the micro level, molecular databases to add potential mechanistic explanations. Hence, by looking at this, acting on the mother food systems requires an extensive body of knowledge and data collection. Unfortunately, current data availability in all these layers is very limited. For instance, we lack detailed data about the food supply and the dietary patterns for the majority of the planet, hampering, our ability to forecast health crisis, see the pandemic, for example, but think in terms of obesity pandemic, and compare different public health solutions worldwide. Why this is important? Well, when you have improved data availability and quality, these tools lead to objective metrics, reproducibility, and informed decision-making. And this is in line with the philosophy of the Sustainable Development Goals set in 2015 by the UN, and is also the focus of my current work with Acumen and Rockefeller Foundation. So now I will show you how, by analyzing the statistic patterns observed in food composition data, we can create tools to characterize food supply quality and suggest intervention strategy with minimal impact. At the beginning of our journey, so some months after, we discuss why we care about nutrition, we ask ourselves a very simple question that you can read here: how much nutrient is in a food? Okay, so we started by collecting the nutrient profile of all foods in the American food supply. And here, for example, you can see, the nutritional profile of raw onion as reported in the USDA, and the concentrations per 100 grams of this product, of this food, cover 8 orders of magnitude. And this range is driven by the complexity of the biochemical processes responsible for nutrient production and modulation. This type of ranges are typical of biological processes. So we're bringing basically nutrition and food composition back to the realm of biology. While this question seems trivial and simple, it is not. And, finding a mathematical rationale behind nutrient concentration got us on the cover of Nature Food that you can see here. So we proceeded in studying how each single nutrient is distributed across the food supply, as plotted here for vitamin B12, okay, thiamine, zinc, gadolinic acid, and total protein. The probability Q that you can see written here captured the food source variability for a single nutrient. Yet, we haven't found any guidance on its expected functional form. Despite the noise and batch effects, because believe me, for sure, the US food supply is not a random sample of foods, so not the best data to work with. We saw, a common pattern emerging. Long story short, each nutrient seems to be characterized by a similar functional form in the log space. Pay attention, this is the log space, only translated at different average levels of concentrations. So we find that log normals, what you can read here, with very similar logarithmic standard deviations, seem to be the best to describe the observed distributions, allowing us to rescale all nutrients and compare them on a single plot, as you can see here. Moreover, we have also observed a cleaner behavior for simple ingredients like fruit and vegetable. And we have also recently confirmed the results in metabolomics experiments on plants. And these results will be shared publicly very soon. So the observed common scale of fluctuations in the log space, followed by all the nutrients, suggest a methodology to detect outliers. So the patterns of different nutrient outliers, as we are seeing here for onion, is then informative of the type and extent of processing. So this implies that we have found a natural metric of processing. Our findings from the mathematical realm connect to the increasing attention to ultra-processed food in the scientific literature. There are different and multiple definitions of ultra-processed foods, from NOVA classification to SIGA classification. And these are all in lines with the theory that there is not just one diet for everyone, and different ethnic group basically evolved to tolerate a different type of diet according to their environment. So a diet as an ecosystem and also as an evolutionary process. So there is a lot of personal and group variability worldwide, but the main common thread is to avoid ultra-processed food. From a chemical and physical standpoint, ultra-processed food is as far as we can get from the diet of our ancestor, the diet we evolved to tolerate. And so not only the standard chemicals that I presented to you before are in weird proportions or combinations, but also there are many alien chemicals such as additives. So according to our observation, there are clear chemical physical fingerprints characterizing ultra-processed food and processing in general. That implies that food processing systematically and reproducibly alters the nutrient concentration in food. And this makes it an ideal application for machine learning. So leveraging the patterns of nutrient alteration in food, I created a score, FPRO, based on the prediction of a random forest algorithm. You can complicate it as much as you want, and then project it, thanks to linear algebra, to a one-dimensional score. This algorithm takes as an input the nutrients concentrations, and the score is in good agreement with classification like NOVA, as we can see here on the right, by following the colors. So we have unprocessed, processed, and ultra-processed food. However, nutrient concentrations give us more granularity, allowing us to discriminate between products otherwise considered identical. See here all these things in pink, right? So here you can see a sample of the US food supply ranked by FPRO. And we can follow how an ingredient, so onion, that we've been following since the beginning, can be, progressively, processed and altered with increasing FPRO. Moreover, well, the algorithm is very fast and adapts to different sizes of nutrient pollen for nutrition facts. So we can work with grocery stores up to hundreds of nutrients. So we can work with clinical studies. Oh God, what just happened here? Okay, sorry, Microsoft was not working. So why having a continuous score is important? Because we can study the variability characterized in different food categories and suggest alternatives within the same group without drastically changing the dietary habits and pattern of the individuals. Indeed, we tend to choose within a limited number of food categories, and our diet is better captured at this level of granularity. For example, I can be, breakfast cereal person and variate my choice of, cereals, but I will never or very rarely consume eggs in the morning. This type of diet modeling led to the What We Eat in America classics that you can see here. And there are basically groups of foods with similar nutrient content and usage. And here I'm showing, all these classes ranked by the median processing score FPRO. For example, let's look into breakfast cereals. Well, we observe an increasing pattern of FPRO determined by the several nutrients alteration, so from here going to here, like the decrease of fiber content, the sugar addition, the fat addition, and the vitamin and mineral fortification. So these cereals would be considered equally ultra processed by some of the epidemiological classifications such as NOVA. And before implementing, going to the field and implementing a food substitution strategy, we investigated the association of our score with several phenotypes. First, we extended our score, a measure for single foods, to a measure of the overall diet. We created two schemes, a gram-based version that is very important to test chemical exposure, so for example, pollutants, and a calorie-based one. We tested this measure in an environment-wide association study that you can see here, or EWAS on NAINS, that is a survey, comprising of more than 400 different phenotypes, from biological aging to vitamin bioavailability and metabolic syndrome. And we prove a remarkable predictive power, as you can see here. So we developed basically a similar pipeline also for the nursery cell study that was published in Nature Communication, where we tested all the nutrients and all the foods available against coronary heart disease. So once quantified the association between FPRO and health phenotypes, we implemented basically an isocaloric substitution strategy, fixing the food categories consumed by the individual to limit the impact on their diet. To minimize, the dietary shifts, we identify within each diet the items with high caloric contribution, but at the same time, for which there are also significantly less processed alternatives within the same group. So by changing, here you can see the number of dishes substituted. So by changing one single item per person in the US population, we already see results. So overall, there is a shift, as you can see here, on how processed is the individual diet of Americans. But we can also estimate in here the implication for the odds of metabolic syndrome, the bioavailability of vitamins, and the concentration of contaminants like bisphenol A in their urines. So to implement in real life something like this, consumers should be empowered with information on the degree of processing characterizing the foods they buy and the available alternatives. So building on the idea of minimal food substitutions, we mined the website of 3 major grocery stores, collecting more than 50,000 products with nutrition facts and ingredient list, and calculated their FPRO from their nutrition facts. Our characterization of the food supplies as several use cases, as you can read here in our mission. So we can assist public health officials in testing food substitution strategy for dietary guidelines. We can empower consumers to choose less processed option without drastically changing their diet. And we can monitor grocery store supplies and define standards of quality. In this regard, the project was recently awarded first prize at the Think for Food Call for Ideas in 2021. That is a prize organized by the European branch of the UN Sustainability Program. This line of work also got me selected for what I'm currently doing with Rockefeller Foundation and Acumen, and is basically about a leadership program aiming to rethink the food systems, from a data-driven standpoint. These are the locations of the store we collect information from compared to, the US population. The long-term goal here would be to leverage, geolocated grocery store offering as a live monitor for public health. We started by expecting basically the top 10 grocery chains in the US by revenue in 2021. And this list is dominated by Walmart, that you can see here, with, with more or less grocery sale around almost $500 billion. And basically a store everywhere in the US. And then we also consider Whole Foods, currently under the umbrella of Amazon grocery stores, with sale around $200 billion. And finally Target, with sales around $21 billion. This is what you see here is the webpage of our pilot currently available at truefood.tech. There is a whole, let's say the goal here is really to have a more transparent way to talk about food, where we show different level of information for those who want to learn more about the products. And following the minimal substitution strategy, here we are classifying food according to categories. Sorry. This was not supposed to happen. Okay, let's move on. Something is stuck. Okay, there we go. So to introduce you to the score, I compare 2 products. In this case, 2 cheesecakes. On the website, there is an introductory page on yogurts. As you can see here, for 2 cheesecakes, we have basically the nutrition facts compared. And the lines in this nutrition facts in specific calories and sugars, they tell you where these items are compared to all the other products in the cake category in terms of calories and sugar. Be mindful that the score that you see here is a percentile related to the cake category. The absolute score that you read here, FPRO, right, is basically telling us that we are very close to 1. That means that we are definitely not talking about raw ingredients or fruit and vegetables, right? We have access to the dairy ingredient list because we mined this from the websites. So basically, we were able to compare them. And here we structure basically the ingredient list that first we compare as Venn diagram as trees. This is the tree for the less processed version of cheesecake, and this is the tree for the more processed version of cheesecake. And here you can appreciate the complexity of the second cake, right? Compared to the first one. We are also highlighting the presence of additives in red as they are classified by the FDA. So finally, if you selected, for example, the second cheesecake, we would have offered you less processed alternatives that you can see here in the switch recommendation tab. So we're done for today's talk. I am aware I have exposed you to notion from very different fields. And indeed, I firmly believe this is the essence of the Foodome project. And this is a body of work that would have never been possible without a considerable interdisciplinary effort. Here you find the publications that I touched in today's presentation. In part 1, you find all the work related to biochemistry, the biochemistry of food, precision medicine and nutrition. In part 2, you find the work related to machine learning, public health, and nutrition epidemiology. And many more papers are in preparation, so I'm more than happy to talk about them if there will be the chance. Thank you so much.
Thank you, Giulia. A great talk. Very interesting, this encounter of complex networks and AI. And it's very interesting also that you were able to use deep learning, so you have enough data to do so. My first question is, did you try other machine learning techniques, or the only one that really worked was deep learning?
So we are learning from, let's say, other random forest models that, for example, were used on features. For example, there are databases that are implementing this type of machine learnings that have been around for, let's say, 10 years or more. But usually they use a mix of features that are not only structural features, but also based on the literature. They generally work decently well when you fix, let's say, a specific protein, a specific target, and you try to learn basically which ligands are binding to that specific target. So they don't work well in an extensive way. This is really where, we needed to upgrade the models, right?
Thank you. John Ortega has a question, I think.
Yeah, I put it in the chat, but I guess, would you mind sending me an alternative to cheesecake, please, or healthier ones, maybe?
Well, we can go back. So it depends where you're buying it and what you are. Well, this is really where we're going. So currently on the website, you can search for cheesecake, and then basically we can give you an idea on the 3 stores for the 3 grocers that I mentioned of what is currently available. And again, healthier, again, it's a big jump, right? We are trying really to bring the narrative on the less processed. And here, then it's a matter of what the medicine is what type of medicine is gonna happen in the next years. But really, then there's this whole ecological and evolutionary discussion of what process is doing to our body, and can we even do processing in the right way, right? If we learn the mathematics behind this.
Okay, thank you.
Joe, you have a question, Joe Fitzgerald? Joe, are you there? Oh, he is now on the train, so cannot. So let me see if so. His question is his comment is exciting research and well explained, great presentation. I'm wondering how your work might be applied to agricultural industries How would you overcome the cultural economic barriers to adoption? For example, agricultural scientists have known the benefits of intercropping for a long time, but the industry still favors monoculture.
Well, I can definitely see. I could say like some of the benefits would be a wider and more diverse chemical profile. So the benefit of having something different from monoculture is really like we can easily connect this, for example, to the thriving of the gut microbiome, right? We're still really much fighting and understanding which are the chemical, especially phytochemicals, that are really interacting with our gut and from a signaling standpoint. So there is a cross-kingdom type of signaling. And while we're trying to figure this out, what is clear is that the more diverse is the chemical profile of your diet, even from a plant standpoint, the better is basically the healthier is your gut microbiome. So this is, I would say, is the first evidence that would push towards diversifying the type of cultures.
Thank you. Usama, would you like to ask a question? Okay. Anyone else would like to pose a question to? So David Button has a question. David, you want to do it yourself or I'll read it? He says,
I'll do it. Great talk.
Thank you.
A lot of information. I will actually be writing this up, so I may have to reach out with some follow-up questions.
Absolutely, I'm more than happy.
How does this? You talk about you're studying American stores. How does this relate to different cultures and diets? Because Americans do enjoy their processed foods, but other countries may not have the same reliance on unhealthy cheesecake.
Okay, so this is a great question. So as an Italian, I can tell you that unfortunately, our kids are probably among the most obese children in Europe, following from a world standpoint in terms of statistics, the United States. So the food supply is changing everywhere. So what we're learning currently on how processes the food supply is a lesson that should be learned, I would say, worldwide. On the other side, from a cultural standpoint, I think that this perspective on diet that is very much related to ethnic groups and cultural habits should give us the possibility to look into our old recipes from a mathematical standpoint as a ideal chemical fingerprints that was selected together basically with cultural groups, right? And so understanding functional foods as well as traditional recipe from a chemical standpoints can really be the driver to, for example, even more effective drug combination therapies.
Thank you. Chandra.
This is fascinating. I have a question which is kind of related to David's. So you talked mostly about processing foods, but I don't know if you've heard of the FODMAPs diet, where they look at fermentable oligosaccharides, and they're looking more at short chain carbohydrates and different structures of food rather than different processing that is done to them, and how that is good or bad for people. Do you have any opinions on that? What do you think of that?
So I'm not an expert, but I can tell you that I think it strongly connects to the concept of food matrix and the food matrix effect. And again, this is a matter of dealing with food, not just from a energy standpoint, but thinking about food as a network of chemicals and biochemicals working together to define a system property that is this going to be healthy for this specific person, okay? And so we are available that according to the chemicals and the structure of the food that surround a specific nutrient, a specific chemical, the bioavailability of the chemical will change drastically. Unfortunately, to have an ideal, beautiful network model that can actually model that, we're still lacking a lot of data. We're still trying to figure out what is the list of chemicals in food. we don't even have a good sense of how they are interacting, right? So these are, the principles of complex system theory. So I definitely hear like there is a lot of merit in what these people are trying to do. We have to get extensive data in order to come up, as we said, with a good modeling of processing and so consistently of food.
I have to say that I've been playing around with the food, your prototype, and it's already fascinating. I think I'm going to be spending a lot of time on it.
Oh yeah, and believe me, this is like, as I said, is a prototype, and so as any model in machine learning should be considered reliable according to the data training that we have. So the more chemicals we measure, the more data that we are able to label, the better this food's going to get. And on the other side, also, how reliable are these nutrition facts? We rely on what people are reporting, what is mandated by FDA. If you look into the fluctuations that are allowed on those nutrient intake by law, it's crazy, right? And on the other side, these are drivers number one of the health in the United States and worldwide.
Thank you.
Yeah,
Thank
Ken,
you.
you have a question? Maybe the last one.
Yeah, well, I was just thinking that it's my hunch is that people are getting heavier almost everywhere. I don't know if that's really true or not.
Gavin, sorry, I'm struggling to hear you. Getting what? So could you repeat,
heavier?
Heavier.
Heavier. Okay.
People are gaining weight almost everywhere. And after World War II, there were some places where people didn't have access to as much food as they would want to eat. And I know that people in China, for example, and even in my family from Europe, that people were taller than their grandparents. And I wonder if the world would be better off if we didn't have access to more food than we should eat. I'm wondering if it's, I mean, you're suggesting that it depends which foods we eat, but I wonder if it's just how much we eat.
Oh, well, that's for sure. So quantity it's something that is part of the, of the main axis in which diet is influencing. So caloric restriction is one of the mechanisms that is taken into account as a way to, intervene on people. Not like there are also different paths related to the type of additives that we are currently putting in our food that are for example, regulating our hormonal system, right? So that is something that it could not be simply taken into account by restricting the number of calories. Actually, the food industry is very smart, as every time. Whenever we point to one specific bad guy, in this case, calories, they give you stuff that is zero caloric, right? Or if we're pointing to sugar, they will give you something that has no sugar in it. So again, the point here, I think, is to shift the model from blaming one specific aspect of diet to try to take into account multiple ones. And that's why there is an effort in data collection, for sure.
Great. Thank you, Giulia, for an amazing work. And
thank you for inviting me.
Yes, and before leaving, remember that we have our next distinguished speaker series on European Union ethics in, let me see, that will be in exactly 2 weeks. So please attend, and thank you, Giulia, again.
Thank you so much for having me and for all the questions. I really appreciate them.
Bye.
Bye. Bye-bye.